Hello everyone! We already had a shader that transformed an image into an old photograph, and this time we'll take this effect to the next level. I'll show how a similar approach can be used to simulate an old film played through a low-quality projector, meaning that various visual imperfections will also change over time. Let's get started. So, just like almost every time, I'll create a new scene, drop in the usual image from our game Whispers of Prague, and apply a shader to it. So let's right-click the scenes folder, of course, create a new scene. It should be a 2D scene, and let's call it Vintage Film. Okay, and I'm dragging the image fountain JPEG into it. So the Sprite 2D node was automatically created, and in the inspector, I'll do the usual stuff, expanding offset and canceling centered, expanding transform and resetting position to 0, 0. Okay, and scrolling down to the material section, I'll create a new shader material, click it, and add a new shader, type shader, mode canvas item. The name is vintage film GD shader, and I'll change the folder to shaders and create, and clicking again to open it in the shader editor. And as before, we'll start by deleting what we don't need in this tutorial so that only the fragment function remains, deleting vertex and deleting light, Ctrl S to save. Okay, so it's probably best to say right from the start that this tutorial belongs in the category of highly complex effects, so I decided to split the video into two parts. Another reason is that this time I'll most likely break my personal record for the number of uniform parameters, because the first part alone will contain 15 of them, which is about the upper limit of what's still reasonably manageable in a single video. In the second part, which I'll publish next time, I'll add another 10 parameters, and thanks to this unusually high number, the shader will be quite configurable. But enough talking, let's get to work. I'll start with the main parameter that will control the global speed of the entire effect. Let's add it here, uniform float. Speed with a hint range, and the initial speed I'll set to 1, and the range can go from 0 to, let's say, 5 with a step point 0, 1. Okay, for the sake of clarity, it will be better to add the remaining parameters only when they are actually needed. Right now, we'll want to add functions for generating pseudo-random numbers, which form the basis of all the chaotic elements that we'll be using a lot of in this shader. And to save some time, I'll simply copy them here from one of the previous shaders. So let's expand this window and paste them just before the fragment function. As you can see, as usual, the names are #11 and #21 in this shader, which simply means that, float input parameter and the float output value. And here we have the vector2 input parameter, and we always get the value from 0 to 1. Okay, so now let's move to the fragment function, where I'll write the usual code that we start this function with almost every time. Let's just get back and scroll down to the fragment function. So this will include defining the UV coordinates, calculating the resolution for some effect layers, and finally a time variable for animations. It looks like this. So first vec2 UV equals UV, then the resolution, which we'll take from our background image, vec2 resolution equals 1 divided by texture pixel size, and finally float time is simply time times speed parameter. Okay, now I'll add the rest of the basic code, reading the value of the current pixel and displaying in the output variable. So vec4 color equals texture function applied on the texture and our UV coordinates, and outputting that color is simply color, simple as that. Okay, so we now have a finished foundation, although it doesn't do anything particularly interesting yet. We'll perform all calculations in separate functions to keep the code more readable and to make it easy to enable or disable individual visual effects. First, let's take a look at simulating the typical image shaking, often caused by old projectors. I'll call this function addShake and place it before the fragment function right here. Void addShake and the parameters inout, vec2, uv, and float time. Okay, as we can see, I once again use the in-out prefix, which allows the changes to the color variable, no color, UV, sorry, to be passed out of this function into the fragment function, from where we'll call addShake function. And so we don't forget, I'll immediately add the corresponding line before the definition of color right here. Okay, so add shake and the parameters are UV and time. All right, of course, we don't see any change yet because the addShake function is empty. I'll go back to it, and first I'll add a slow and smooth drift in both the horizontal and vertical directions. We can achieve this easily using the sine function with different frequencies. So let's do this. UV is increased by vec2, and now I'll put that to the separate lines for clarity. Sine time times, let's say, 0.7, and the second component is sine of time times 0.5. Okay, and the semicolon. All right, so as we can see now, it is a bit too much. So let's divide the result by 100 right here times 0.01. Wait for it. Okay, much better. Now it's moving only slightly. However, it's typical for all projectors that the image shakes a bit more abruptly, so we'll add new uniform parameters to control the jitter. So I'm scrolling up to the uniform parameters section and adding them. Uniform float jitter x with a hint range, and let's set it the default value to 0.4, and the range goes from 0 to 1 with the step 0.01. Then the second one for the y direction, uniform float jitter y, another hint range, and the initial value, I think 0.2 was selected during my experiments, and again from 0 to 1 with the 0.01 step, and finally the speed. Uniform float jitter speed hint range, and the speed I think I set to 12, and it goes from 0 to, let's say, 20, again with the step 0.01. Okay, as usual, I'll use randomly chosen constants to increase the pseudo-random factor. And because we want these fluctuations to occur in all directions, I'll remap the results to the range from -1 to 1, like this. So let's scroll back to the addShake function, and I will add the corresponding lines. Float jitter equals floor of time times jitter speed divided by jitter speed. So there are some more discrete jumps, And the UV vector change. UV is again increased by. And vector 2, and again, I'll just put it to two separate lines. The first component is hash11 of jitter times 7.3, just random numbers, plus 1.1, for example, and just ignore it, please. And the remapping minus 0.5. I'll try to type faster so we get rid of this strange effect. Times 2 times jitter x. Okay, this is the first one, and yeah, thanks to the compile error, it's not jittering anymore. What exactly? Yeah, of course, the comma. And now the second line, hash11 of jitter times 3.7, for example, plus 2.5, and again minus 0.5 times 2 and times jitter y will fix it because it's a pretty slow value, but not exactly. I think we need to divide by 10 again, so times 0.01. Wait for it. Yeah, let me show more of that. I'll just zoom out a little bit. Now it's jittering much better. The final improvement in this section will be a simulation of the shaky transition between frames on the film strip in the vertical direction. We'll achieve this by imitating a lower frame rate and setting the probability that the film strip will jump. Two new parameters will come in handy for this. So scrolling up to the parameter section and I'll add them. Uniform float. Let's call it roll chance with a hint range and initial probability 0.04, and it goes from 0 to 1 to this with the step 0.01, and the uniform float roll amount, another hint range, and the amount 0.08, so it doesn't jump too much too abruptly. And this time I think, yeah, let's keep it as it is, from 0 to 1 and 0.01. And now we can complete the add shake function, scrolling back to it and to the end, with the lines that will do exactly what I just described. So I'll just write them. Float frame ID equals floor of time times 16. So we are just narrowing it down to roughly 16 frames per second. And now we'll simulate the rolling up and down. Float roll on equals step of 1 minus roll chance value in the hash11 of frame ID times 0.05 plus 5. Okay, so this is the first pseudo-random factor, and now similar for roll off. Roll off equals hash11 of frame ID, and this time times 0.09 plus 9, just to give it another pseudo-random value, minus 0.5, and everything is multiplied by 2. Okay, and now we can change the y-coordinate of the UV vector. uv.y equals modulo of uv.y plus roll on times roll off times roll amount, and the modulo is by 1. Okay, wait for it. Yeah, have you seen the occasional jumps? Now it happened. Okay. I think it works. And I think the result looks quite believable. The image shakes and occasionally jumps up or down. Uh, the image shakes and occasionally jumps up or down, which is enough for our time-based coordinate changes. All the following functions will therefore affect only the color of the resulting pixel, so we'll place them in the fragment function after the definition of the color variable. I'll get back to that, and after this we will place everything else. By the way, if the constant shaking becomes distracting while we continue working, we can temporarily disable it by commenting out a line where we call the add shake function. Let's do it. Control K, and it's commented out and it's not shaking any longer. Great. So, as the first filter, we'll add a color transformation into a typical sepia effect. I'll therefore add a function called addSepia with the color parameter because we won't need anything else inside it. So let's scroll up a little bit, and right before the fragment function I will add void addSepia with the parameter inout vec4 color. Okay, and I'll insert a call to this function into the fragment function right here when I made space before. Add sepia of color. Cool. So how do we implement it? Once again, we'll need several uniform parameters to control the intensity of this effect. The fading of the original colors through a reduced saturation, and also the tint of the resulting sepia color. So the parameters will look like this. Scrolling up, and I will add them. Uniform float. Sepia amount with a hint range and the initial amount 0.75, and the range again goes from 0 to 1 with the step point 0.1. Now the second parameter, saturation, uniform float. Saturation, okay, hint range and 0.6 I think was the good initial value, and it can go from 0 to 2, for instance, again with the step point 0.1. And finally the color tint, uniform vec3 tint color. This time we don't need the alpha channel. Source color, the hint for the color picker, and the initial value vec3, I think the values were 0.95, 0.88 and 0.72 for the typical light brown tint. Okay, let's return to the add sepia function. Here it is, where the first step will be changing the color saturation by converting the image to grayscale and blending it with the original color. So float gray is the well-known formula with the dot product, dot of color RGB, and vec3 0.299, 0.587 and 0.114. You may remember from some other videos that I made this value another uniform parameter, but I think it's definitely not necessary this time. We already have enough of them. And to use it, color.rgb equals mix of the original color RGB and vec3 of the gray value. Gray, okay. And the mixing factor is simply 1 minus saturation, because we want to do it in the opposite direction and desaturate actually. Okay, now we can see definitely a difference. Let's open shader parameters and change the saturation value. It's overly saturated. Now it's not at all. So let's get back to 0.6. And the second part, the sepia effect itself, which is actually a very similar calculation, just with different parameters. So let's do it here. Vec3 sepia equals tint color times the gray value. Okay, and again, color RGB is another mix of color RGB, sepia, and sepia amount should be our parameter. Wait for it. Of course, there is something wrong. So again, sepia. What exactly is not recognized there? Color, another typo. Okay, sepia amount. Now it's found, and this is it. Wait for it. Yeah, very nice sepia filter. That completes this function, and we can move on to the next one, which I'll call add flicker, because it will handle the irregular flickering of the image, something that is also typical for these projectors. This happens when the stroboscope covering the light source is no longer perfectly synchronized with the film strip due to wear and tear. And because this is a moving effect, this time we'll also need a time parameter. So the function skeleton therefore looks like this. So right after add sepia and before the fragment function, I will add void, add flicker, and the parameters in-out, vec4, color, and float time. Okay, and once again, so we don't forget, we'll immediately insert this call into the fragment function right after add sepia, add flicker with parameters color and time. All right, so how do we achieve irregular flickering? New uniform parameters will help us, again, allowing us to control the speed, amount, and contrast of this effect. So let's add them. Scrolling up and adding the parameters. Uniform float, flicker speed with a hint range and the value, initial value 6, I think. Okay, and the speed goes from 0 to, let's say, 10 with a step point 0.1. Then uniform float. Flicker amount, another hint range, and the initial value 0.2. And this time the range goes from 0 to 1 with the step point 0.1. And finally, the contrast flick, uniform float, contrast flick, hint range, and 0.1 as the default value. And yeah, again from 0 to 1 with the 0.01. Cool. And now the function itself. The algorithm consists of obtaining a pseudo-random frequency using a combination of several calls to the #11 function and then blending it with the corresponding contrast. Once again, I used various randomly chosen numbers and the result looks like this. Okay, so float flick time is simply time times flicker speed parameter, and let's calculate the flickering itself. Float flicker is 1 plus #11, too many ones, sorry, of floor flick time, okay, plus 0.1 minus 0.5 times flicker amount. Okay, I know it's getting a little bit complicated, but the result will definitely be worth it. I think we can put this line to the second line and do the third line in the similar way. So I'll just copy and paste this line and add a semicolon and do some changes. This is the same, but we are multiplying this time by 2.3 times 2.3, and instead of subtracting, I will add 1.7. Okay, hash floor flick time. Yeah, sorry, the bracket should not be here, but okay, I think I didn't simplify it at all. Let's just scratch it and write it from the scratch. So hash 11 of floor of flick time times 2.3, because we are simply composing this effect from several octaves. It's similar to the fractal Brownian motion, but a bit simpler. Plus 1.7 minus 0.5, just make sure you have all these brackets correctly, and times flicker amount times 0.5. Okay, yeah, this should be correct. And finally, let's incorporate the contrast. So float contrast equals 1 plus hash 11 of floor of flick time times 1.7 plus 4.1 minus 0.5 times contrast flick parameter. Okay, and now we can change the color finally. Color.rgb equals color.rgb minus 0.5 minus, I said, 0.5 times contrast plus 0.5 and times flicker. Okay, yeah, it's definitely flicking. We can see that the resulting image really does flicker with a certain degree of irregularity. And again, if our eyes start hurting from it, we can temporarily comment out this line and move on to implementing the next effect, which will be a slowly moving horizontal highlight, also known as a scan line. So let's just scroll down and I will cancel it temporarily. Great. So the scanline. Here I should probably mention that scanlines are more typical for old televisions, and we wouldn't really encounter them much on a movie screen. So if you need an authentic 100-year-old projector effect, you can simply omit or comment out this function later. However, it's a very simple algorithm, so I ultimately decided to include it, and everyone can decide for themselves. Alright, so what do we need? First of all, parameters, surprise, for controlling the speed, strength, and sharpness of this effect. So let's add them. Scrolling up again and adding a uniform float band speed with a hint range and the initial value 0.35, and the range goes from 0 to 2 with the step point 0.1. Then the strength, so uniform float band strength, hint range and 0.12 as the default value, and the range from 0 to 1 with the step point 0.1. Okay, and finally the sharpness, uniform float band sharpness with a hint range and the initial sharpness, let's set to 6, and it can go from 1 to, for example, 20, again with a step point 0, 1. All right, and now the function itself. It will differ from previous ones in that the calculation requires both the pixel color and its coordinates. So we'll add another input parameter. This time I'll write the entire function right away and then insert its call into the fragment function. So scrolling down, and right before the fragment function, let's do it. Void add scan with parameters inout, vec4 color, vec2 UV, and float time. Notice that I used the inout prefix only for the color and not for UV because we are not supposed to change it. The only change we needed for UV was in the add shake function. Okay, and let's write it out. So float band y, as it's supposed to be only moving in the y direction, equals modulo of time times band speed parameter and 1, because the UV coordinates go from 0 to 1, as we know. All right, now let's define the stripe shape. Float stripe equals exponential of a negative argument. We know that from previous tutorials. It simply means that it will have a pretty smooth edges, which resembles this kind of stripe pretty well. Okay, and now inside the pow function, uv.y minus band y, this is underscore, times band sharpness times 3, and the argument is to the power of 2. Okay, and semicolon. Great. And finally, the change of the color. Color.rgb is increased by, because we are adding the stripe to the image, stripe times band strength times, and let's give it another tint, not exactly the white, so 1.95.8. Okay, so the function is finished, and let's call it. So scrolling down to the fragment function, and right after add flicker, which is currently commented out, let's add scan, and parameters color, UV, and time. Okay, and yes, can you see it? We have this line over there, and it's doing exactly as expected. Okay, and since we reached the announced 15 parameters, I'll stop here and leave everything else for the next video. We can still take a look at how the complete effect currently looks if I uncomment the commented outline. So let's uncomment add flicker and add shake. And yeah, now it's shaking, flickering, and the scan line is over there, and also the sepia effect. Great. Thank you very much for watching. You can probably guess that I saved all the scratches, stains and burn marks, which we could see at the beginning of the video and which are probably the most characteristic features of old films, for the second part of this tutorial. These are slightly more complicated functions, but I'm convinced the final shader will be worth all the effort. Until then, take care, good luck with your projects, and we'll definitely see each other in the next video.